Sorry, Neil.
Sorry, Neil. We're kind of getting in the middle of this one here. All right. We'll see if he actually watches. So now this is kind of nice because these are just both x squares, and I could multiply everything through by 400 if I want to. Might not be a good idea without a calculator, but well, 400 times 16, we're probably going to have to do it anyway at some point here. But I could add this over. If you don't like fractions, that's probably a smart thing to do, is to multiply by 400. Okay. If you don't mind fractions, you'd add that over to this side, so you get negative 16. And then we add a 400th. So 1/400th added to a negative 1/200th. What's that? That'd be negative 2/400ths plus 1/400th would be negative 1/400th x squared. Now, see, you're still going to have to multiply 16 by 400 anyway. What's 16 times 4? 64 plus add 2 zeros. Negative times negative is positive. So this is going to be 6,400 equals x squared. So x is 80. That worked out nice. And they usually will on the no calculator. So x came out to be 80. So we know that this point is 80. And then we can get the y value of that by plugging that into here. So 80 squared, that's 6,400. 6,400 divided by 400, we just said was 16. So 100 minus 16 is 84. So that's that point. Now, what does that help us know? Slope. Oh, but to be honest, we knew slope from derivative, right? So I wouldn't have had to do that. I could have just put the 80 in there, right? So I could have put the 80 in for the x right there, or I could just do the slope between these 2 points here. Either way. It comes out to be negative 2/5, I believe. Or a decimal would be okay. Negative 0.4 you could do. But if I take that 80 and I put it in for that x, or I do the slope between these 2 points here, I get negative 2/5. So that's the slope of that line. So now, and since this is the y-intercept, I can do my point slope form, but what the heck, since I got the b, the y-intercept, I'm just going to use that. So I get negative 2/5 x plus 1/16, right? So that is the equation of this line. So now all I need is to do what? Set that equal to 0. I need to find where does that y touch the ground here. And so I just set this equal to 0. Now again, we'll have a little bit of algebra to do, some arithmetic really. So I'll subtract 1/16, I have to multiply by 5/2, and so you'll have to multiply that out. But it comes out to be 290. So this point comes out to be 290 and 0. And then what was this point back here? Where'd the parabola hit the ground? Yeah, that'd be negative 100 times by 400. That'd be 440,000. Square root of that is 200. So this hits at 200. So how far is it between there? 90 feet. So things work out pretty nice. But the Shanghai thing, and what is that? It's when you have a tangent line and you know another point on that tangent line. That's the Shanghai thing. You don't know where, most of the time on tangent line problems, we know the point of tangency. They say find the equation of tangent line when x is 7. So you know the point of tangency. So you do the derivative, plug in a 7, you get the slope, get the point, away you go. In problems like this, we don't know the point of tangency. So we have to call it xy. Well, we need another point. And when we have a second point, then we can do this Shanghai thing. We can do the slope between 2 points, set it equal to the slope or the derivative. And then that usually gives us the information we need. Okay, so Shanghai doesn't seem so bad anymore. Right? It's getting better. Getting better. All right. There might be some other ways to have done that, to approach it, but they all end up being kind of the same thing. You still need the derivative. We could have done a tangent line equation earlier, put this derivative into it, put our point into it. We could have come up with some things there, but in the end, it still would have, somehow this would have still been involved. That slope between 2 points and the derivative idea. Okay, let's go to sample 2. Let's go to sample 2. Hopefully you got a chance to get started on some multiple choice ones there. Somebody brought up 11, the mean value theorem. That is something that we have not learned yet. There's very little that we haven't learned yet as far as the midterm goes. There's a couple of theorems here at the end of chapter 4 that we're going to learn as the week goes on, and that's one of them. So 11 we'll say. But I think that might have been the only one. All right, any others? 10. Okay? At how many points in this interval does the instantaneous rate of change, what do you think of when you read that? Instantaneous rate of change. Derivative. Derivative. I mean slope at a point, but that's what derivative is, right? Slope at a point. So that's derivative. So instantaneous rate of change should make you think derivative. What's average rate of change? Slope between two. Average rate of change should make you think slope between two. So it's a little bit like Shanghai right here. Derivative equals the average rate of change. It's kind of the same thing. All right. Now, from that standpoint. Now, here's the function. Now, it would be good. This is no calculator. It would be good if we knew something about this function. When I see negative a and a, I think about even odd type functions. You're putting in opposites. Negative a and a. Those are your endpoints. So let's talk about this. If you put in opposites, what kind of function do you have here? Is it even? Is it odd? Is it neither? And does that matter? It's an even function, I think. If you put in a and square it, you get a squared. You put negative a in and square it, you also get a squared, right? Negative a times negative a is a squared. So you put in two opposites, you get out the same thing. So this is an even function. Well, what is the average rate of change on an even function? I mean, here's an even function right here. It has y-axis symmetry. So if you get the same thing out, what's the slope between those 2 points? 0. Between any two. Slope between those 2 points. 0. So what this question is really asking is, when is this derivative equal to 0? That's what it's really asking. Now let's say you hadn't thought of that. Let's say you didn't think even odd function, and you didn't think about that idea. Let's say you just decided to set that up. So you said, okay, instantaneous rate of change makes me think derivative. So derivative of this would be what? E to the x squared times 2x, right? And that's got to be equal to the slope between 2 points. There's your 2 points right there. So what would be, how would I do the slope between 2 points? Remember, that's y2 minus y1, although I don't really like that way of doing it. How have I said we should think about it? I don't like that notation. I'd rather use function notation. What would that look like? F of b minus f of a over b minus a. That's when our endpoints are a and b. What are our endpoints this time? Negative a and a. So tell me what to write. I'm going to write it like this. I'm not even going to plug that in yet. Let's write it F notation first. F, but I don't want to use B because let's use the ones we're given. So let's go F of negative A, F of A over negative A minus A, right? Okay, now let's do what you were saying. Now let's plug in, let's do F of negative A. So let's plug in negative A. What do we get? E to the a squared, right? Because negative a times negative a would be a squared. All right, minus f of a. What's f of a? Same thing. Oh, okay. And then the bottom is negative 2a, right? So what is this right here? 0, right? So without even thinking of that even odd thing, if you just did slope between your 2 points, so if you did f of negative a minus f of a, and right, but the key is being able to do this F notation. So here's a great example of why I was telling you earlier that I'd really rather you think of your slope between 2 points in this format as opposed to y's and x's, because you might not have known what to put for your y's here. Now, hopefully you thought to plug an a into the function and a negative a into the function to get your y, so maybe you would have, okay? But that's what we get. Well, we can see that's 0. No matter what a is, it's going to be 0, but that's what we said. No matter what a is, the slope between those 2 points is always going to be 0. Okay, so now it's just a matter of solving this. So with all that said, it ends up being just this. So when does that equal 0 or when does that equal 0? Well, when's this equal 0? Never. Right? Right? E to the 0 is 1. Right? So this is never equal to 0. And then when does this equal 0? when x is 0. So how many times does this happen? One time. When x is 0. Okay? All right. Keep in mind, there is a scale in the midterm test. There is a scale. I'll look it up, and before we get to the test, I'll look at it. I don't think you want to worry about that so much, though. You don't want to think, well, I need to get this or I need to get that. But the reason I tell you about it is so you just understand the difficulty level, right? An A might be a 65%, right? So you just have a sense that, oh, geez, I'm doing horrible. I'd be lucky to get a 65. Oh, hey, that's an A. Oh, okay. Well, maybe I'm not doing so bad. I'm only getting half of these right. Well, that's a B. Oh, okay. You know what I mean? So it's that mindset you got to have.
What's the highest you've ever gotten on
going in? I have to look that up. I mean,
Parental challenge.
there's two different parts. I mean, there'll be two separate grades. The midterm will go in as two grades, two 30-point quiz grades, basically. So the highest raw score, I suppose 90 maybe, 80, high 80s, 90s maybe, something like that. So I have to look it up. I'd have to look. It might be a little higher than that. Might be a little higher than that. Okay, what else? We got a little bit of time. We could probably do one more. Yeah. 7. Oh, this is good. This is a good one.
I don't want to do it.
This.
Wait, I can do this.
This you should be able to do without any work shown, with a picture in your head, and you know the answer is C. Is that the right answer? Did anybody look it up? That's what you got? How'd you get it?
First I tried substitution.
Okay.
0 over 0, so I kept going. I picked a number really, really close to 0, but not quite 0.
With a calculator or without a
No,
calculator?
without calculator, just
It's like .001 or something.
yeah. And no matter, it doesn't really matter what you pick because it's always going to equal that number over itself. I let x equal 3 because it's its own problem, and then I'll just
Right, and that's fine. So you turn this into 3.0001 minus 3 all over 0.0 like that.
Makes sense.
Yeah, I am puzzled. No, I'm thinking of a problem where that your reasoning would have failed you.
I'm trying to think of a way where you might be wrong. Oh, who is different part?
I like the reasoning. No, I do. I like the reasoning because that's what we talked about. I mean, we talked about as a limit problem, you try substitution. 0 over 0 means keep going. Try something close to 0. You can't use a calculator, so you try something really close to 0. You look at it and so forth. Now, what happens sometimes is when, especially without a calculator, when you look at something really close to 0, because what you're saying is, okay, the absolute value of this is just 3.001 minus 3, so that's 0.01 over 0.01, so that's 1. So for this particular one, that line of reasoning would work. If I change that, I believe, to another type of function, like a sine function or something like that, then we would run into a lot of difficulty. In other words, if I would have changed, let's just change this function to sine of x plus h minus sine of x. Now, notice how this looks very much the same, right? So now if we put a 3 in there and a 0.001, so now we have sine of 3.001 minus sine of 3 over 0.001. Correct? Now we have difficulty there, right? Because we don't know what sine of 3.01 is minus sine of 3. And so that would be tough. So good. Got a 1. If this was the test, who cares? You don't have to show any work, right? It's right or it's wrong. So if you got it, and you move on. Even if you guess, right? Because guessing is allowed. Used to be, did I tell you about that a couple years ago? Guessing was not allowed. In other words, there was a penalty like the SAT. They would take off points for guessing, but not anymore. So guessing's okay. Now, does anybody know why they do that? Or how they do that?
Yeah,
Have you
how
ever
do they know if
had
you
explained?
guess?
Well, it's not that they know that you guess it.
Just getting it wrong.
It works like this. Here's their rationale, and it's actually pretty good reasoning. Here's an example that I would use to give. This is worth talking about, and then we'll get back to this problem here. It used to be on the AP test until about 2 years ago that there was a penalty for guessing, just like they do on the SAT. Now, here's why that is. It depends on the way they do it. Depends on how many choices there are. If there's 5 choices, like on the AP test, then they take off 1/4 of the value of the problem for each one you get wrong. If there's 4 choices, they take off 1/3 of the value. Now, here's why and the mathematics behind why this works. If you gave the calc test to a first grader, they should get a Z. Well, most first graders. When I was in first grade, no. First grader should get a 0 on the calc test, right? But if you told them to take the calc test and just fill in bubbles, what would they get if there were 5 choices? Theoretically, 20%. They'd get 1 out of every 5 right just by guessing. Okay, so their score would be 20%. That is not an accurate reflection of what they know. And you would think the score is supposed to be an accurate reflection of what you know. So they would say on multiple choice, you should penalize or you should take out the guessing component. So here's what they do. To make this easy, let's say each problem's worth 4 points. Okay? And let's say there's 100 questions. So if that was the case, a first grader, by guessing, would get how many of the 100 right? They get 20 of them right. And they get 4 points for each one, they would get 80. Now that's 80 out of 400, that's a 20%. But what they would do is they would get 4 for a right answer, they would give you 0 for a blank, and they would give you minus a 4th, so if they're worth 4 points, they'd give you minus 1 for a wrong answer. So you lose a 4th of the value of every right answer. So that means for every one that they guessed and got right, the other 4 that they missed, they lose a point on. So the 4 points they got for getting one right, they lose 4 points for the other 4 they missed, and that balances out. So this person who got 20 of them right by guessing would miss the other 80. They would lose 1 for each of those, and so their score would be 0. So the idea is that corrects for the guessing component and gives a more accurate reflection of what you know. Now, here was the dilemma. As I would teach and get ready for the midterm and the calc test, people would get really freaked out about that negative. And they would be afraid to answer. If you weren't really confident, you'd be afraid to answer because you would lose points. Well, you don't want to leave them blank either, though, because you don't get any points for that. So it gave this whole game of should I answer it or should I not answer it? Should I take a chance and I think I got it, but I don't know. So I think eventually they decided, let's just take that out of there. We'll just raise the scale a little bit, knowing everybody's scores. So they looked back at statistical data and said, okay, the scores are going to be about this much higher if we take away that penalty. And then they just went with that. So the scales have been raised a little bit as far as what's acceptable, what's an A, what's a B, and so forth. But they've taken away that penalty, so we don't have to worry about it. Okay? So that is kind of the lesson on that. So let's come back to this now. So there's no penalty for guessing. So you did that, you got a 1. You weren't really guessing, but you reasoned through it, seemed reasonable, so you got a 1. And you'd get it right. Okay, now let's talk about what we should have been thinking on this one. This problem, the H should give it away. We haven't talked about this for quite a while. What is this limit right here? Yeah, it says H approaches 0, but what does this stand for? Oh, come on, it's the most important. That's a definition derivative. That's the long way of doing derivative. And remember we did those worksheets where when you look at this, you're supposed to identify what the function that this is the derivative of. And the key is you look right here where the x plus h is, that must be where the x was, right? Where the x plus h is. So what function is this? This is the absolute value function. So we all hopefully know the absolute value function is this. At 3, what's the slope?
1.
1. Okay, 1. Now let's come back to my example over here. If I gave you this same problem in a no calculator situation, my hope is you look at this and say, hey, that's just derivative. What's the function? Sine. What's the derivative of sine? Cosine. So what's the answer to this one? Cosine of 3. So that would be the answer to that. And that would be one of the choices in that problem. So the answer to this one would be cosine of 3. Okay? So, important lesson, because this shows up a lot. This limit shows up a lot in these no calculator packets. Okay? When you see that, it's not a limit problem. Don't think of it as a limit problem. Think of it as a derivative. This is the definition derivative. Think about what the function is, and then so the question really is not limit, but slope. What's the slope of that function? What's the derivative of that function? Okay? And so that's how we would do that. Okay, we need to move on today, but we'll come back and we'll do some more with sample 2. Matter of fact, that's part of your homework for today, is to do some more in sample 2. But we do have something to talk about in the book, so some notes, maybe some things to write down. We're going to get started with it. We won't have time to finish it today, but this is section 4.6. I don't think this is actually something that Newton came up with. I think it's just more named after him because it uses his ideas of, that he kind of discovered that became calculus. He's one of the co-founders of many of the ideas that became calculus. And so it's more of a situation where it's kind of named after him. But it's finding zeros of a function. Now this is kind of, we're going to take a day, the rest of today and some of tomorrow. It's a little bit of a history lesson. Because a lot of this, well, it's kind of interesting because some of the things we study or used to study, we don't study anymore because of technology. We don't spend as much time doing paper pencil types of things, long division, those kind of things, because of the calculators and the things we have available now. So we just don't spend as much time on it. Now, we lose something in that, I think. Some number sense, some arithmetic ability. I mean, I think we lose a little bit, but I think we gain as well. So it's a trade-off. It's kind of like you don't spend near the time in elementary school doing penmanship as we used to, because we don't handwrite things that much anymore.
They're not even teaching cursive.
I know they don't hardly spend time teaching cursive. I mean, think about the hours they spend writing out that stuff like that. And now when I go to write it, about the only times I write in cursive now is when I write out a check. And it's awful when I write out a check because I got to stop and think about it. It's been so long since I do it. I just don't do it very often. We type so many things. And everything I do here is printing. And I write quite a bit just because of what I do here. But it's all printing. And so anyway, so things change as time goes on. Well, this is interesting because Newton's method, what's funny is Newton's method kind of came into importance more because of technology. In other words, I never learned this when I was taking calculus in high school. I never learned it in college when I took calculus. Because most of what we need to work this is pretty labor intensive. But Newton's method is actually programmed into, or a variation on Newton's method, it actually plugged into your calculators when you do the solve thing, right? We all love the solve thing on our calculators, right? Well, without this, the calculator couldn't do those solve things. I mean, we just look at it as magic. But somebody had to program. Somebody had to program the process for these to be able to solve those equations.
No, it's magic.
And this is this is it. I mean, this is similar to what's in your calculators, a little more basic version of what's in your calculators to do the solve. So it's really worth studying at this point. Okay? So now, we're going to start to investigate this a little bit. So zeros of a function, what's that mean?
Zero.
Where it's input or output? Output is zero. Where the function crosses the x-axis, basically. Now again, we're going to pretend we're like 100 years ago. All right? And all we got is paper, pencil. Now we're going to cheat. We're going to use our calculators for add, subtract, multiply, divide, and help us with that a little bit. Okay? But otherwise, we're going to kind of pretend, hey, this is 100 years ago, and I've got this function right here that I would like to find the zero. X cubed plus x plus 3. Right? Now, 100 years ago, and hopefully today, what do we know about a function like this? How many times is this going to cross the x-axis? No more than 3. Is it possible it never crosses?
Yes. No. It has to cross on one end because
It's an odd function. It's got to cross, or it's an odd power. It's got to cross at least once. If this was 4th degree, it's possible it would never cross.
Yeah.
This has to cross at least once, but it might cross 3. But we don't really know. We can try to graph it, plot points, whatever. But again, with a graphing calculator, bam, we just go solve and just know. We could graph it and right away get a pretty good estimate. But all those 100 years ago would have been a lot harder to do. So again, put yourself in that mindset where we can cheat and use a calculator a little bit here, but not to graph, not to solve. What could we do in a guess and check kind of way? It doesn't even factor. I purposely picked one that didn't factor. There were some. What we're trying to do is set this equal to 0 and solve it, right? Well, it doesn't factor. So guess and check. What can we do? Yeah, that doesn't really do us any good because if you subtract 3, factoring doesn't work unless it's equal to 0.
Start with 1.
Plug something in. Yeah, literally. Let's just plug numbers in. Let's try. Yeah, so we're going to go from a really long way of finding this root to a hopefully shorter way. Now today we're going to have the really long way and then a maybe not as long way and then, maybe not as long, whatever. But let's try plugging in a 1. What do you get?
5.
You get 5, right? Plug in a 1. 1 plus 1 plus 3, we get 5. Well, what were we hoping to get? We're hoping to get 0. Shoot. Well, we didn't get it. Okay, what else you want to put in? -1, yeah, it's smart because you certainly don't want to put in 2. That's just going to keep getting bigger. So right? So this is a thought process. Though. Okay, so put in -1. What do we get? We get 1, right? -1 plus -1 plus 3. So we get 1. Well, that's closer to 0, so we might be on the right track. What can we try now? -2.
Shut up. Don't do it.
Let's try -2. That'd be -8 plus -2, that's -10 plus 3, -7. Well, we still didn't get 0, but what did we just learn?
It's a fraction.
It's got to be between them, right? We just went, and now, again, several concepts that we've learned here become pretty important. Number 1, we know this is a continuous function. So we know this function didn't just jump from 1 y value to a -7 y value, right? We know it didn't jump, it's continuous, so we know it had to cross through the x-axis going from positive to negative. So we know that the root, and we don't know how many there are, but there's got to be at least one. We know there is a root between there and there. Okay, but now we're getting into decimals and fractions. Now it gets kind of messy. Because now we could say, well, let's try this. -1.5, right? Now, you try that and you say, oh, I'm going to have to cube that. Oh, man, I'm going to have to work that out by hand, right? And that gets kind of long. But 100 years ago, they wouldn't have thought that because they did everything by hand. So they just would have done it without complaining. Because they weren't lazy bums like you guys. Okay, no. So,
I knew you were going to say something like that.
or me too. I mean, come on. But oh, yeah, that's right.
Especially you, Neil.
So, yeah. So it would get tough. And let's say we wanted to get it to 3 decimal places. I mean, think about how hard that would be to do that. Now, especially if this is cubed, and it would be virtually impossible if this was sine function. You have to look up on a sine table, and then you have all this other stuff you have going on. Okay. Now there are some other tricks then. So what do? Right? What are the necessities of other invention? So what that means is they'd be rolling along. They said, well, we need something. What would be a simpler way? Well, one of the things you learned about in trig class, maybe it was in algebra 2, something called synthetic division. And synthetic division is a way that you can work with polynomials. It works mostly with polynomials, but where you could plug numbers in to something like this without having to cube it or fourth degree it or whatever, it would be simpler. And it looked like this. I'll do it with -2. You'd put a -2 here like this. You'd put the coefficients of your function. Why'd I have to put a 1 there? Or a 0 there? Because there's no x squared term. So I had to put a 0 in there. And then the synthetic division looked like this. Bring down the 1, multiply there, 0, multiply there, add, and then you add these. That times that. Oh, I did something wrong. 0, 1. What? Oh, no. Okay, I'm doing something. Bring down the 1. Oh, yeah, right here. Yeah, thank you. -2 times -2 is 4. 4 plus 1 is 5. -2 times 5 is -10. 3 plus -10 is -7. And this number right here is that output. Now, it was not that big a deal, but if this was a higher power, and these were weirder numbers, this is a quicker way to find that. So it was something they came up with. That's not something we're going to do now, but it was just another way to find these values. Okay? So these are always, so this is just guess and check. So we know it's somewhere in here between -1 and -2. All right. So again, smart people thought there's got to be another way we can come up with this idea of finding the root. And they came up with this right here. Okay, so this happens to be the graph of this. Now let's say again, 100 years ago, we weren't sure what the graph was. We didn't have the graph, but this worked for any old graph. So here's a graph of a function, and we're interested in that root right there. Okay, so what we're going to do is we're going to start out by guessing. That's kind of what we just did. Okay, so I'm going to guess that this is the root right here. Okay, now clearly it's not because we can see the graph, but if we couldn't see the graph, all right, we're just using this graph as a reference and we're thinking through this process. So I'm going to guess. Now what did we do? We guessed a 1 and we plugged it into the function. So let's do that. So let's plug it into the function, and there it is right there. And here's where this technique brings in calculus. What the people who came up with this method said, what if we drew a tangent line then to that function? That's easy to do because we can plug in and get this y value, so that's easy. We know how to do derivatives, so we could get the slope easily, right? So if I have a point and a slope, I can write the tangent line equation. Now think about what that does for you. When you have a tangent line equation, okay, that's a very simple equation to solve. And remember, back in this day, that's what they're interested in. What are things that are easy to solve? Not cubics that I don't know how to solve, but a line equation is very easy. Where does this blue line cross the x-axis? Well, it'd be when this line equation is 0. And that's a very easy equation to solve, right? So for them, they would do that. So they would write the equation of this blue line. So what would they need? They need the derivative, right? They have their guessing point. Plug it in, get that point. Do the derivative, get the slope, write the equation line, set it equal to 0, and find that point right there. Now, what good did that do? Well, they're going to repeat that process. That's going to be their next guess. So then they're going to take that point and plug it into the function. There it is right there. Then they're going to take that point and put it in the derivative, get the slope. So now they got a point and a slope. They can do a new tangent line equation. And they can draw that tangent line. There it is in green. And then they can see where that tangent line crosses the x-axis. Now, what do you notice?
It's getting closer and closer.
It's pretty close to the point we're interested in, which is where the black line's crossing it. Now, what important concept are they taking advantage of? The one that we learned where when you look at a curve and zoom in, what's it look like?
A straight line.
A straight line. What they're saying is that when the curve crosses the x-axis, if you can get in here close enough, the tangent line is going to cross pretty much at the same place where the curve does. And we don't know how to solve the curve set equal to 0, but we sure know how to solve the line equation set equal to 0. So they repeat this and repeat this and repeat this until they get within however many decimal places they want. Let the line equal 0 and so forth. Now, it's still a long process, but it's something that they could come up with. And all they would be solving is a line equation. And think what you need to solve a line equation: subtraction and division, right? Mx plus b equals 0. You subtract the b, divide by the m. That's all they need is subtraction and division, and they can handle those things. All right, so a couple of issues that can come up with this, though. It's kind of fun to look at, and we're going to run out of time here, so we'll go through this some more tomorrow. Okay, so here's a sine graph. So they could do the same thing. They make their first guess. They plug it into the function. They draw the tangent line. They see where that crosses. They repeat it. They plug it into the function. They draw the tangent line. Look at that. It's already crossing very close to there. Okay, so after only a couple of cycles through, they can start to find this root. Now, what are some issues with it? Well, one issue is, what if their first guess was up here? Like right there. Right? Sometimes Newton's method is thought of as riding the tangent line. You make a first guess, you go up to the curve, and you ride the tangent line down to the x-axis. Well, problem is this one's going to send us way away from the root we were looking for. So sometimes we call that a shallow tangent. If you make a guess that's up near the peak of the curve, your tangent line is going to go way out there. And if you make a guess that's right at the peak, then you really got a problem, because now it's a horizontal tangent, right? So that's really bad. So that's an issue that can sometimes happen with Newton's method. Another one is called cycling. Here you have a curve, and you pick a point, and you draw the tangent, and it goes to there. And then you repeat, and you draw the tangent, and it goes right back to where you started.
Gosh darn.
And then you go to there, and it takes you to there, and you go to there, and it takes you to there, and you just sit here, and you just cycle back and forth. Doesn't happen very often, but it's something that could happen with a bad guess. So what you do is you just make a different guess, right? Just make a different guess, and it'll work. All right? So yeah. So but that's the idea. Okay. So first of all, I want you to understand the process of Newton's method. So back to our problem, and we're going to write this down now. So the long way, and I'm not going to make you do this. The longest way of doing Newton's method would be to do the equation of the tangent line every time. Do the derivative, right? Which in this case would be f prime would be 3x squared plus 1, right? Pick our first guess of, say, -1. Plug that into the f, plug that into the f prime. Get your slope, get your point. Write the tangent line equation, solve it equal to 0, find that point, and then repeat. Plug it into the f, plug it into the f prime, write the tangent line equation, set that equal to 0, solve it. You see what I'm saying? That would be the longest way to do it. We're not going to do that. Okay? Now, you don't have to write this part down, just follow me up here, and then we'll come back to the previous page. So what I'm going to do is I'm going to save you a little bit of that time. We're going to take the tangent line equation, which is this, right? And we're going to do it just one time and see what happens. So here's what I'm going to do. In place of y, I'm going to put 0, right? Because we want to know when the tangent line hits the x-axis. So that's when y is 0. In place of m, I'm going to put f prime. Now, again, you don't have to write this down. In here, I'm going to put x sub 0. That stands for our first guess. So that's our slope, right? F prime. And then here I'm going to put x minus, and now for our first x coordinate is going to be our guess. And then for our y point, we're going to put f of our guess. Right? Does that make sense? So x sub 0, f of x sub 0 is our guess, and f prime is our slope. Okay, now we're going to solve this for this x right here. So I'm going to subtract the f of x over to this side. Okay, which gives me this. Oops. And then I'm going to divide by f prime. Right, see what I'm doing? Okay, so that's gone. And then I'm going to add the x sub 0 over. So I get x equals, and when I add the x sub 0 over, I'm going to put it over here on the left. So I'm going to have x sub 0 minus f of x sub 0 divided by f prime of x sub 0. Now remember what I said? Solving a linear equation is what? Subtracting and dividing, right? That's what we got here, right? Subtracting and the divide, okay? Dividing by the slope. Subtracting the b, dividing by the slope. So this is what we have. Now, what could I label this x then? If this is x sub 0. What do we get when you take that first tangent line and see where it crossed? x1, right? In other words, when we did it here, we called the first one x1. We actually started with x1, and then we called the next one x2, and then the next one x3, so forth. And what's happening? Each one of those is getting closer and closer to our answer. Each one of those is getting closer and closer to where this crosses. Okay, so for you guys, the result of this is we don't have to solve our line equation every time. I've done it. Let me call that x1. This is like our formula now. So this, if you want to write this down off to the side somewhere, okay, this is like our formula. To get our next guess, all we do is take our first guess minus the y value of the first guess divided by the slope of the first guess. Okay? And then what do? We repeat that. We take x1 that we got and we plug that into this. You see what I mean? So this is going to shortcut it for us a little bit. Now, it's still long, but it's definitely easier than writing the tangent line equation every time and solving it every time. Okay? So let's go back to this problem we were doing. So let's say our first guess is -1. Right? Isn't that what we guessed 1, but that was way off. So we'll save ourselves a little bit. We'll say -1 was our first guess. So here's what we would do. If our first guess is -1, we would write -1 minus f of -1 divided by f prime of -1. Okay? So what do we get? What's f of -1? That was 1. And what's f prime of -1? 4. Now we'll use our calculators right now to cheat a little bit. Just use your calculator screen and let's do -1 minus a 4. Oh, you don't need a calculator. That's it. What's that? -1 point. Let's go decimals here. Now we are hoping to get what? Hoping to get 0, right? Where are we hoping to get 0? I'm sorry. Where are we hoping to get 0? Where are we hoping to get 0 right here? We're hoping to get 0 right here, right? When we put -1 into f. So if we would have got a 0 right here, we'd say, hey, we're done, right? That's it. Okay. Of course, if we got 0 right here, this would have been -1 minus 0 would have been -1. Yeah, same thing. Yeah, -1 was it. Okay. This is now our new guess. So my next is this, -1.25 minus f of -1.25 divided by f prime of -1.25. Now, this still seems pretty intensive, but it certainly isn't as bad as having to write, get the slope, get the point, do the tangent line equation, set equals 0 every single time. Okay? Now, we're gonna cheat a little bit. I'm gonna let you use your calculators here. Okay? Now, as a matter of fact, as part of your homework for tomorrow is going to be to finish this problem. Now, there are some things you can do in your calculator to help you start to simplify this a little bit. Now, the one thing you could do is just simply take -1.25 and plug it into f. Write that down. Take -1.25, plug it into f prime, write that down. But what would be something that would shortcut this a little bit? Something on the calculators that I showed you.
Such that.
Define the function, yeah. Define the function. Define f to be this, and well, you can't define f prime. Define g to be this. Define this to be f, and define this to be g. And then you can just type in f of -1.25 and g of -1.25, right? And that would make it a little easier. Okay? Now, tomorrow, I'm going to show you even some more shortcuts on doing this, and you guys may come up with them on your own. And I want you to play with that and investigate that a little bit. Okay? Yeah, babe.
You make another function, like put in the whole thing.
Okay, stop. Just be quiet. Yes, I think I know where you're going with that. I think I know where you're going with that. So play around with that and do that, and that we'll talk about tomorrow. Okay? And don't tell anybody else.
Keep it a secret.
But you know what I'm saying? So what we're doing, again, what's happening here is every time this is our next guess. Now what should start to happen as we get closer? No. This should be getting closer to 0. But what about this answer we get out here?
It's gonna also-
It's going to get closer to being the same all the time. Right? In other words, this is the x-coordinate where it crosses the axis, right? So what should happen is our tangent lines just keep pretty much being on top of themselves. So right here we got negative 1.25. Next time it might be negative 1.237. Next time it might be negative 1.2161, whatever. And pretty soon this decimal place won't change. This decimal place won't change, right? And so then it just matters how accurate do you want to be. Do you want the answer to be 3 decimal places? You keep going till the 3rd decimal place never changes anymore. You see what I'm saying? So that tangent line is getting closer and closer and closer out to so many decimal places. That's what's going to happen. Okay? And so there's a lot of different ways we'll get to see that. But this is called Newton's method. It uses a derivative, and it's a pretty ingenious way of using that tangent line to find the root of a function. Now again, go back. Why were you interested in roots of a function? Well, think about optimization. Where's the derivative equal 0? That's finding the 0 of a function right there, right? So before we had just the old solve button, we had to have ways of solving these equations. And so this was a technique. Now, like I said, when I was in high school, we didn't use this because it was pretty intensive. So we did some other things. Number one, they never gave us a function like this. They always gave us one that factored. They always gave us one that was a trig ratio that we knew and memorized. You know what I mean? They manufactured the problem so they didn't come out weird. Well, now we don't have to do that because we've got this tool we can use. Okay? But then when they started programming those calculators, they said, how in the world are we going to program this to solve an equation? Oh, we can program this. Think about this. You guys are in computer math especially. When you program it, what's a computer really good at? Doing the same thing over and over and over again. You give it a set of steps to carry out, it'll just do them all day long. And that's what this is doing. Okay? And so what your calculator is programmed with is an accuracy that it wants the answer to be at, 10 decimal places or whatever. And when you hit solve and hit enter, it runs through that until it gets that much accuracy. And that's how this is going on. Okay, I'm going to show you some things that I want you to be able to do with Newton's method tomorrow. So for tomorrow, your assignment is this. Finish this problem. Keep going with this. And then work in sample 2. So in sample 2, probably the next multiple choice section at least. Okay, remember we have 2 more packets to come. And we have less than 2 weeks till the thing. So we need to keep going. So let's get working in sample 2. If you still have stuff to get done in sample 1 and so forth, let's use tonight to get caught up because tomorrow we'll have some other homework as well. So finish this and work in sample 2. That's it.